Hello, my name is Marco Martinez. I am an electronic engineer from Bogota, Colombia, and I'm going to talk about visualizing sound as part of the first week assignment of the course Introduction to Music Production. For this, I'm going to be using a small program that I wrote in a software called MATLAB, where we will be able to see, listen, and interact with the different characteristics of sound, such as amplitude, frequency, and timbre. So, first, why visualizing sound? Let's say that you are working with some audio recording, you are producing some music, you are in the digital audio workstation, so you need to somehow relate all those numbers, all those different characteristics, and the best way to do it is with a visual representation. So that's why we have these three types of visualizers: the oscilloscope, the spectrum analyzer, and the sonogram. With the oscilloscope, we will be able to see the signal, the waveform changing in time, its amplitude. In the spectrum analyzer, we will be able to see how the frequency is spread among the spectrum. And in the sonogram or spectrogram, we will see the spectrum analyzer repeated in time. So we can see that in the y-axis of this oscilloscope, we have the amplitude. This can be the voltage or the pressure of the wave, of the sound wave. In the x-axis, we have the time. We cannot tell a lot. We can measure the frequency, but with signals, with very complex signals, they can become very hard. So that's why we have the spectrum analyzer, where we will be able to see the different amplitudes of the different contents of frequency of the signal, but we won't have information about time, of how the signal behaves in time. So that's why we have the sonogram or spectrogram, which basically is a combination of these two. We'll see the spectrum analyzer repeated on time, and that's why in the y-axis we have the frequency, in the x-axis we have the time, and to measure the amplitude we have a color scale where blue is a low value and red is the highest value. So let's see some different sine waves at different frequencies and amplitudes. This was a 100 Hz, 300, 400, 500, and as you can see, I was varying the amplitude and as well the frequency, and these changes were evident in the oscilloscope, spectrum analyzer, and sonogram. In the oscilloscope, the amplitude was decreasing, as you can see. In the spectrum analyzer, the peak of frequency was moving from 100 to 500 Hz, and in the sonogram, this red peak was also moving, and in time was behaving as the signal was behaving. So let's have more examples. So now we can do this with a most complex signals, but before I want to show you this image, this is the sawtooth wave, and this is its frequency content. This is the spectrum analyzer. As you can see, this is the peak obtained by one sine wave, as in the past examples, and these are different peaks. So if I sum all these peaks together, I will have this signal, this sawtooth wave, and this was done by this famous mathematician Joseph Fourier. So you can see it on Wikipedia if you are interested in this topic. So let's construct this sawtooth wave by summing these signals. First, I have my fundamental frequency, the 100 Hz, and I'm going to start adding multiple integers of these fundamental frequencies, but with different amplitude. This is the second one, the 200 Hz. And as you can see, the signal is starting to become sawtooth wave-like. And as you can see, the second peak here. And as I'm adding sine waves to this signal, it's becoming more and more as a sawtooth wave. As you can see, the levels of intensity of amplitude change in the sonogram. This 1400 Hz has this amplitude, and here is represented by the color orange-yellow. And you have the waveform of the sawtooth in the oscilloscope and all the frequency content of the signal in the spectrum analyzer. Well, as a matter of reflection, I use this program and to illustrate better the way of visualize sound, and what better than actually seeing it and interact and listening to it. Hope you had liked it. Thank you very much.